welcome. Hope you guys are having a productive band practice. Our goal for today is really simple. We are going to just take a look at two problems, but I need to make an announcement. The announcement is you're going to have a test on Wednesday on Chapter 7, in which you're going to need to demonstrate your competence in the areas of momentum and collisions and center of mass and all that good stuff. We'll do some review tomorrow, and so that will help. And you will, of course, do some review on your own, because that's what you do, because you guys are good students. Okay, and I actually mean that seriously. I'm enjoying teaching the class this year. I'm getting a lot of good hard work out of you guys. All right, so we're going to be taking a look today at two problems. Number one is going to be 61 from your book, and the other one will be number 17. Let me pull the pictures of those up here. Physics. Oh, and on my lesson plan, pray. I forgot to pray, so we'll do that in just a moment. First, I need to get the pictures here. There they are. That's 70. So this one must be... Oh, come on. Pay attention, please. Sometimes I just feel like I have to beg my computer to pay attention to me. You ever feel like that?
Yeah, sometimes I feel like an email. Sometimes I just think
There we go. That's 61. All right, so we're going to pray, and then we'll get going. God, thank you for today, for your care for us, and for your provision. We ask especially for our friends who are in band that you will help their rehearsals be productive, and we also pray for wisdom and insight into your creation. Amen. A helium balloon and its gondola of mass m are in the air and stationary with respect to the ground. A passenger of mass little m then climbs out and slides down a rope with speed v, measured with respect to the balloon. With what speed and direction relative to Earth does the balloon then move? What happens if the passenger stops? Okay. Yeah, that's right. We hope the guy's wearing gloves.
the gondola
Is the basket. And actually, I don't know of people that take rides in helium balloons. So this is a little artificial.
Aren't they all like the fire thing? Or do they like the
Yeah, that's and the reason they don't do that is the balloons that are using flame are actually ejecting gas out the top, right? They're losing hot air from the little hole in the top of it, and that would complicate our analysis. So they want it to be helium so that the mass doesn't change.
So this is kind of like, oh.
Yeah, right, exactly. That's right. Or like the guy that tied a whole bunch of balloons to his lawn chair and went over.
Balloons though?
What's that?
Aren't those weather balloons and he shot them out with like a shotgun?
Yeah. Yeah. And there was some really weird case out in like Arizona where a kid, like a 6-year-old, did something like that, and it turned out to be the parents were in on a hoax. I can't remember the details. Maybe the parents said the kid did, and then it turned out it was hiding in the attic. Anyway. Yeah, it's hiding in the attic, right? Yes. Crazy things. Crazy things. Yeah, yeah. So, if you think about it, right? So, it's a country of about 360 million, right? So that means a 1 in a million shot happens 350 times. So, anyway, a helium balloon, blah, blah, blah. What are we going to do with this thing? Good. Let's start by drawing a diagram. See, it's just us and our wits against the problem. So, you know, here's our helium balloon plus gondola. And it has mass m. And here is our passenger of mass little, and the rope. That is, the guy is in the middle of sliding down. I don't know why I think it's a guy necessarily. This is definitely a gender neutral scene right here.
Did this happen on like a TV show?
Oh, I'm sure that there's been some TV show about this.
Like, I'm pretty sure Moonlighting had an episode like this.
Okay. Now what? We've drawn a picture. Okay. Definitely want to write down what we know from the problem. What do we know? We know the masses. We've got that. Check. Helium balloon are in the air and stationary with respect to the ground. What does that tell us? They're not moving. Okay.
Or if they're on the ground.
So the velocity is 0.
The one velocity is
Now, I want to actually challenge what you said there, or if they are, the ground is moving too. Because it says with respect to the ground, it's not just that we're going to assume that the velocity of the ground is 0 for the purpose of the problem, it's that the velocity of the balloon is 0 in the reference frame of the ground.
Right, so if the ground is moving too, then the velocity would be 0.
Exactly. Right. So it's not that you were incorrect, I just wanted to be clear in thinking about it. Passenger of mass m then climbs out and slides down the rope with speed v. What speed and direction does the balloon then move? So let's process this carefully. When we said velocity is equal to 0, what were we really talking about?
Velocity adjusted to
Yeah,
Velocity in the water.
yeah. But what's up with this?
bubble.
Yes, that's right. We needed some before and after going on here. So our diagram actually represents, is this representing the before or the after situation? The after, right? So we're actually going to need to put that the guy is sliding down with speed v, and we need a separate diagram for before. And it's pretty clear what's going on here. The diagram for before should show our gender neutral sphere in the balloon. V is equal to 0 here, and V. So I've got a before and after situation.
So Mr. Keel,
Uh-huh.
in a accelerated reference frame, if the guy was staying still, would the balloon be moving up with the V?
Well, that's an interesting question, because that actually happens at the very tail end of the problem, right? The passenger stops. So he stops going down. So now the question is what happens with the balloon? Okay. Now that we've got our before and after, we want a physical sense of the problem. What is your physical sense as to what's going to happen with this balloon of mass capital M as the guy slides down?
Then the balloon will go down as well.
Okay, so your physical sense is the balloon will go down as well. So we'll have like a V1, something like that. One down.
Like whenever they throw the bags out the side of the thing with extra weight, it pulls down to the balloon. You know what I mean?
Okay. All right, so a little bit of experience there. Experience isn't really a physical principle here. What physical principle should be guiding our thinking? Experience is not a bad thing, right? But we kind of wonder if your experience there is going to translate to the experience here. What physical principle should be guiding us?
Center of mass.
What about the center of mass?
Or the lady and the guy on the face when she pulled herself.
Yes, that's right. So now talk to me about center of mass. What can we say?
being lowered. That's the guy who's doing
It's being lowered. What outside force is lowered?
it. The man moving down because the mass is spreading out.
But he's not an outside force, he's part of the system. And so here's where the big principle has to happen. The key to unlocking the problem is to compare the before and the after and to ask yourself, what has to be true about the momentum of this system? Yes, exactly. The momentum of the system is 0 before, and since there are no outside forces that are going to be exerting any impulse on this, the momentum has to be 0 after. Well, what about gravity? Let's think about gravity carefully, because gravity is an outside force that's acting right here. What if I take the Earth and include it in my system? Now, gravity is no longer an outside force, and the Earth isn't moving. I think we can all agree that the Earth is not going to be moving in this problem here, at least relative to the Earth. And so now gravity is essentially a force that cancels out from the before and after situation. Really how we're thinking about it. And as a result, the center of mass of this system should not move. Well, if that's the case, then what should it rise? It should rise. That's right. Our experience was wrongly applied here. Excuse me. Our experience was wrongly applied here.
Oh, because I got it. Since mass is being let out, the balloon is going higher.
Yes, exactly. That's right. We just threw a man-sized sandbag overboard. And now, now the balloon has got to go up with it. Okay. There it is. Now that actually gives us more than just a qualitative understanding, it gives us a quantitative understanding. Because how do I express mathematically that the momentum of the system has to remain 0?
Because these are equal but opposite.
Is that really true? Wouldn't the momenta be equal but opposite?
The momentum.
Right. Really, I want to start with an equation that expresses the fact that the momentum before equals the momentum after. Really, I just have to write down. It's like that.
So P initial equals P.
That's it. Go.
P MB equals, or MB plus MB equals 0.
There you go. But now we're troubled a little bit by some wording in the problem. And that is that this guy was sliding down a rope with speed v measured with respect to the balloon. And what's weird about that is that up until this moment we had been using the Earth as a reference frame, right? With respect to the ground. And now all of a sudden they want to measure it with respect to the balloon.
So what is PP V minus V1?
Yeah, exactly, that's right. So we are, what we're going to end up with is a V with respect to the ground instead of with respect to the balloon. How could we fix that? How about let's just fix it by going ahead and biting the bullet and finding the speed with respect to the ground. And then we'll come back and we will find the speed with respect to the balloon in just a minute. Okay? Does that make sense? In other words, what we're doing is what we call in computer science lazy evaluation. We're going to put off doing the hard thing until later, and we'll solve the problem we can solve right now. In math, we call this, I wish this were an easier problem. And I do that all the time. So we're going to solve the problem that we can solve now. And that allows us to immediately determine that V1, the speed of the balloon, is equal to the opposite of Vg times this ratio little m over big M. Think of it as almost a conversion factor.
Mr. Gable.
Uh-huh.
So you divided by negative m?
Yes. Uh-huh. That's right. Yeah.
What is VG?
Vg is the velocity of the guy sliding down with respect to the ground. Because everything in the problem was given to us with respect to the ground, except for V was given with respect to the balloon, which we thought was weird, and why are they doing that? And we'll go back and fix that in just a second. Because they want a final answer relative to Earth for the balloon moving. So we've got our answer, except that it's in terms of this variable that we don't know what to do. Okay? Does that make sense? So that was actually a fairly easy problem so far, in as much as it's a simple matter of conservation of momentum. Momentum was 0 before, so momentum has to be 0 after, so we add up and there we go. The only problem is we've got this Vg, and we need to come back and fix it. But actually it's not a problem at all, because you have the right of it. If you think about it very carefully, the velocity of the fellow with respect to the ground, the velocity of the man with respect to the ground, should be equal to the velocity of the man with respect to the balloon plus the velocity of the balloon with respect to the ground. But the velocity of the balloon with respect to the ground is this V1. And the velocity of the man with respect to the balloon is V, according to the problem.
Is VMG the same as VG?
That's what we call VG. Think about this intuitively so you can see what I'm saying. What happens is, this guy is going down the rope. I'll try to draw this for the sake of our listening audience here. So this guy is sliding down the rope with a certain VG downwards, right? And as he is sliding down the rope, at the same time, the balloon is carrying him upwards a little bit, V1. And so the velocity that he has going down is being partially counteracted by the balloon going upwards, carrying him upwards at the same time. Let's do it for instance. Let's say he's sliding down at 5 meters per second and the balloon is rising at 1 meter per second. Then, if he's sliding down at 5 meters per second relative to the balloon, and the balloon is going up at 1, then relative to the ground, he'll only be sliding down at 4. You see it? So the velocity of the balloon takes away from him. And we didn't talk about relative velocities much, but the way that you think about it is really like this, that you add in the velocity of your reference frame to the velocity of your old reference frame to get the velocity of the object in the new reference frame. So coming back to here, then, I can substitute and then it's a matter of simply solving. And we can solve, we're looking for V1, so we're gonna get all of our V1s on one side and all of our V's on the other side. And so we can do that by distributing and adding to both sides. And a little bit of factoring, because factoring is our friend. And this gives us V1 is equal to that right there. What do you think about the form of this answer? It is messy. What would you do to clean it up? Think of slogans that I often repeat. What's the messy part about it?
Other fractions.
Yeah, and what do I usually say about fractions?
Division is just multiplying the reciprocal.
Division is just multiplying by the reciprocal. That's one way to think about it. And another way to think about it is, if I have compound fractions or fractions that offend me in some way or another, clear them out. Clear those fractions. And how do we do that? By multiplying both sides, the top and bottom, by common denominator. And the common denominator here is capital M. And when I multiply top and bottom by capital M, and the top is canceled so that I get little m before v. And at the bottom, we get m plus capital M, just like that. Yes?
I figured out that it's capital times times.
Now, that's good. So this problem turned out to be complicated because it had two different simple problems packed into it, and we had to handle those simple problems separately. The first simple problem was conservation of momentum, and that was actually easy. 1, 2, 3 lines. Boom. The weird part about the problem was dealing with two different reference frames. And what alerted us to the fact that we had two different reference frames was the fact that the problem was set up with respect to the ground, and then halfway through the problem it switched and did with respect to the balloon. You see what I'm saying? And so we handled that fact by simply ignoring the with respect to the balloon at first. We solved the problem just with respect to the ground, and then we came back and we put in the reference frame shift to make that happen. How are we doing? Okay. I was looking at you, I couldn't tell if you were bored, sleepy.
No, I think that
Oh, yeah. Yeah. Understood. Okay?
Wait, did we ever figure out what
was
the state of the balloon?
Well, tell me. If he stops. Yes, that's right. The balloon has to stop too.
Oh, yeah.
Exactly.
Negative M times zero.
That's right. Right, you can see it either in the equation, if v becomes 0, then boom, the balloon stops. Or you can also see it from the fact that momentum has to be conserved during the entire thing, and since initial momentum is 0, that determines the process for forever. Now, interesting question. He comes to the end of the rope and he lets go. What happens now?
The balloon continues to go and falls to the ground.
Yeah? That seems weird. Why does the balloon continue to go up?
He leaves the system.
He does leave the system.
Changing reference frame.
Yeah. Yeah. Changing reference frames, we're also changing the system, really, at that point. When he leaves the system, now the buoyancy force on the balloon takes over, essentially, dominates the gravitational force. And at that point, the balloon is now going to rise up according to its own sum of forces, essentially. And meanwhile, the man is now going to drop according to his own sum of forces. And the two are essentially decoupled. They're no longer in the system. All right, let's take a look at number 17. Oh, that's exciting.
That's true.
Wasn't a good professor. It's the one that started this whole problem. You just stayed in the balloon.
That's right.
That's good rope climbing skills.
On the way into school, Kayla was asking about, she asked, well, what is calculus anyway? Yeah, just because she knows I teach calculus, right? So I was explaining to her that calculus is essentially the math underlying the description of all motion that we have. So it's built into the structure of everything from like moonshots to cars to whatever. And then that led to, well, what is algebra? And so I tried to explain that algebra is essentially the math that you're using to try to capture word problems or real-life situations. And she said, can you give me examples? So for example, you go to the store. Here I'm trying to think fast. And I said, for example, you go to the store and you've got hammers and you've got saws and you've only got storage space for 15 of them. And the hammers cost $12 and the saws cost $20 and you've only got $200. And so now the question is, how can you essentially maximize the number of hammers and saws given those constraints? Well, so we can actually assign variables, x and y, to the number of hammers and saws and all that. She said, or you could just go ask your friends to hold the hammers and saws for you. Okay, yes, you could do that. She's thinking outside of the dots here. And I guess we could deconstruct all the physics problems, right? The way to solve number 61 is to tell the guy to stay in the balloon, darn it. Okay. Number 70 is actually a kind of classic problem, and we have a name for this. We call this a ballistic pendulum problem. And up until recently, this was, in fact, the way that forensic scientists would determine the muzzle velocity of a gun. I say, nowadays they have a similar kind of system, except that I believe they use springs to determine the amount of force or the amount of energy of the bullet, rather than this kind of system right here.
It's more like ballistic gel or something.
Yeah. The ballistic pendulum that's described here actually led to the invention of rockets. It was Goddard who challenged orthodoxy a little bit. It was believed that rockets were going to be impossible because if you get out above the atmosphere, then the rocket would have nothing to push against. That was the common thinking. Just as an airplane is unable to fly above certain height because it has no air to actually provide lift for the wings, so also it was believed that rockets would need to be able to push against it. Goddard said, no, actually, the rocket is going to be pushing against its own exhaust gases. And to demonstrate this, he set up a rifle in a vacuum, and he used a remote wire to trigger the rifle, and when the bullet went this way, the rifle went that way. Conservation of momentum. And so it's ultimately conservation of momentum that powers the space shuttle, or the launching rocket for the space shuttle that now no longer flies. In that, you have these exhaust gases at tremendous velocities going out the back end. And as a result, because of conservation of momentum, the rocket has to rise in the front end. So, in some sense, Every time a rocket fires, the entire momentum of the whole system is zero. Yes,
So was Goddard the guy not like a businessman that's in Maryland?
based upon,
Yeah.
right?
I was figuring the
So
name.
Goddard Space Center, like named after him. Bullet is fired vertically into a 1.4 kilogram block of wood. If the bullet has a mass of 29 grams, that's a heavy bullet. That's a really heavy bullet. This is like a musket ball. Actually, it's heavier even than that. This would be, I don't know what this would be.
That would do some real damage.
Small can.
But
It's okay.
that's essentially an ounce. Okay, and it's got a speed of 510 meters per second. How high will the block rise after the bullet becomes embedded into it? The one thing you do want to notice, what do you notice as you look at this problem? Anything that you're going to have to pay attention to? Yes?
Oh, no, don't say people are into the drugs and grams.
Bing, bing, bing. Very good. We have a winner. Always watch for that. You got your units that are mismatched. We're going to have to convert that. And when I do, I actually do it kind of automatically. How many kilograms are we talking about? 0.029. So I just write that in and cross off the original, so I don't have to mess with it. Okay. The thing that is slightly tricky, I guess, about this is that we need a before and after scenario, right? But actually, we're going to, if you look carefully, you have a little bit more than that. The bullet is fired into a block of wood at rest directly above it, right? So that gives me my before scenario. And I can draw that pretty easily. Here comes the bullet. Here's the block.
You do it vertically.
Well, the bullet is fired directly into, vertically. Thank you. Yep. We have to read the problem correctly. So actually, I need to take this back. The way that the forensic stuff is done is the bullet is fired horizontally and the mass swings like this. This is a little bit different.
So can you not use the special formula for realistic time zones?
I don't recommend trying to memorize special formulas.
Yeah,
like
I'm just
that.
asking for this problem.
Yeah, you would not be able to, right? I don't recommend trying to memorize special formulas for special cases. It's better to derive it for yourself, to walk through the process, how that formula comes about. And in the process of deriving it, you will then understand under what circumstances it could be used. If you're thinking as an engineer, and I know you tend to think as an engineer, engineers will look up special formulas, but in so doing, they have to make sure that the circumstances are appropriate for that formula. And that's why deriving the formulas is really most useful. Let's go ahead and write our masses in here. 9.
It's pretty sturdy block.
What's that?
It's pretty sturdy block of wood.
It will probably experience a lot of damage. The bullet will become embedded, and it will splinter the wood as it goes in and so forth. So this is what we call destructive testing.
Still seeing this bullet's a hollow point and not an explosive thing.
Ha. Now, if the bullet has a mass of a watt and a speed of 510 meters per second, how high will the block rise after the bullet becomes embedded into it? So we're actually given the speed here. Now, here is our before. What does the after look like?
Does that still speak on the wood?
They do, that's right. Okay.
And then they have a velocity right now.
They're going to have a velocity going up. That's right. But what's slightly weird about this is that it then asks, how high will it rise? Which is strange because the whole rising part happens after the after part. You understand what I'm saying? All I'm doing is talking about how we break the problem down verbally. And so what we're going to need to do is to actually have before And after, with respect to our collision, so this is before and after collision wise, and then we're going to have some kind of final state in which the block has reached its maximum height. And what's true about the block once it's reached its maximum height?
What else do you
The
do?
velocity is zero, that's right. And it's going to be above, so let me actually draw it. So this guy has now gone up to a height of h. Yes.
Two things. So, so you'd have, the momentum equal the same on those, the before and after, or the before and after?
Yes, that's right. For the before and after, the momentum is going to be the same. How do I know that? Because in the before and after scenarios here, there are no outside forces acting on it, or they are negligible, because the collision here happens so quickly. So let's go ahead and do the computing on that. That's actually fairly easy. We've got 0.029 kilograms times 510 meters per second. Equals combined mass 1.69. Nope, wrong. 1.429 kilograms. Make sure we did that right.
You just run with 1.43.
I would hold off on the rounding until the end. And the reason is that, yes, you are right. It really would, round, but we want to do the rounding at the end. We want to avoid round-off errors if possible. And so when the dust settles, we end up with total momentum is only 14.79 kilogram meters per second. And when we divide by 1.429, we get 10.3 meters per second. I want you to notice how remarkable this is, and actually, this is fairly large only because the boat is really massive. We went from 510 meters per second, or about 1.4 times the speed of sound, something like that, to 10 meters per second, 25 miles an hour, 22 miles an hour. And all of that is because this bullet here hit such a much more massive object that the whole thing just gets slowed down. It's going to lose a tremendous amount of kinetic energy in the process. We can estimate the kinetic amount anyway.
Somebody's reading like shattered.
Yeah. Yeah.
In other words, you need to draw a free body diagram for the after so that you can find out the.
Yeah, yes, exactly. We need to do free body diagram, or my favorite would be energy analysis. Energy analysis is probably superior to trying to do Newton's laws here, because we have a conservative force, gravity, that is taking away all the energy of our system. So let's do that. Let's say that the kinetic plus potential here and here we'll call this the after state has to equal kinetic plus potential in the final state. Notice that I couldn't really do that in the before state. I could not use the kinetic energy of this guy because most of that kinetic energy gets lost or wasted in the collision. But I can do it as I go from here, this state, to that state, because the only force acting is gravity, a conservative force.
So what's you?
U is potential. I know your book uses PE, but I use U because the whole purpose is to do that. So let's see, what do we have? We have 1/2 of mass times speed squared equals 0 plus mgh. notice that the masses actually cancel out. So that what I'm left with is 1/2 of 10.3, yeah, it's pretty close to 10, that's right. So the height that I get then is 5.3 meters. Which is fairly impressive. But I want you to notice how profound this is, because since the masses cancel out, what that tells me is that any object that is moving vertically with a speed of 10.3 meters per second will rise to a height of 5.3 meters. Whether it's a flea or an elephant, as long as air resistance is negligible. I guess it wouldn't be a flea. But as long as air resistance is negligible, then any object with this speed will rise to that height. And actually, since we have like 1 minute, we can prove that statement very easily. If I have a speed at the bottom with a certain kinetic energy to it, then all of that kinetic energy gets converted into potential at the top. And since the masses cancel out, notice that the height that we end up with is always v squared over 2g. So that the speed uniquely determines how high you will rise. Yes?
That's when we figured out the spring law, right?
What's that?
That's when we found out the spring law, right?
Yeah. All right. See you later.